There is a sound that has no medium, a tremor that requires no ground. It is the final desperate chirp of reality itself, strained to its absolute breaking point. For 100 million years, two ghosts have been waltzing in the impenetrable darkness between galaxies locked in a death spiral of their own making. They were once gargantuan stars burning with a ferocious light, but their lives were too brilliant, too massive to last. They collapsed under their own impossible weight, punching holes in the very fabric of the cosmos, leaving behind not matter, not energy, but an absence. An absolute perfect nothingness with an appetite. Two black holes, each one a gravitational titan, a scar on the face of spacetime. And for eons they have circled one another, an ineluctable countdown set in motion by gravity's patient hand. With every pass they drew closer, the space between them churning into a violent vortex. They bled energy, not as light, but as invisible vibrations, subtle tremors that rippled outwards at the speed of a light, carrying away the momentum of their deadly dance. Imagine the universe as a vast, silent ocean, and these two monsters are spinning faster and faster, whipping the water into a frenzy. Now, in the final milliseconds of their existence as separate beings, they are moving at over half the speed of light. The distortion of space-time around them is no longer a gentle curve. It has become a screaming, terrifying singularity in motion. Time itself for an observer caught in their grip would slow to a crawl, while space would stretch and squeeze like taffy. And then, the final impact. It is not a collision in any sense we would recognise. There is no crunch of metal, no explosion of shrapnel. It is a moment of pure, unimaginable violence, a fusion of two regions of infinite density into one. In that final fleeting instant, this merger unleashes more energy than all the stars in the observable universe combined. Yet not a single photon, not one glimmer of light escapes. All of that power, all of that fury is released in a single, deafening blast of gravitational waves. A tsunami of space-time distortion races out from the cataclysm, compressing and expanding everything in its path. This is the tremor you are feeling now. A wave that has travelled for over 1 billion years to reach you, its power diluted by unfathomable distance, now so faint it warps the space inside your own body by less than the width of an atomic nucleus. It is the ghost of a scream from an event of cosmic annihilation, and for almost the entirety of human history we were utterly deaf to it. We stood on the shore of that cosmic ocean, blind and numb as these titanic waves washed over us, completely unaware. Our eyes, the most sophisticated instruments of discovery we possessed, were useless. They are built to capture light, the electromagnetic echoes of cosmic events. A supernova, a nebula, a distant galaxy, they all shine. They announce their presence with photons, messengers. We learn to catch first with our own biology, then with telescopes of glass and steel. We built an entire science, a complete model of the universe, based on this single narrow sense. It was like trying to understand an opera by only reading the libretto. We saw the actors, we knew the plot, but we could not hear the music. The grand sweeping symphony of gravity, the true soundtrack of the cosmos, was entirely beyond our perception. Because gravity is different. It isn't a force that travels through space. Gravity is the shape of space. When a massive object moves, it doesn't send a signal out into the void. It forces the void itself to reshape, to ripple, to transmit the news of its motion as a shudder in the fabric of reality. These shudders, these gravitational waves, are not like light. They are not easily blocked or scattered or absorbed. They pass through planets, stars, and entire galaxies as if they were nothing, carrying an uncorrupted, pristine message from their violent source. They are the universe's most secret, most intimate form of communication. To hear them would be to gain a new sense, to suddenly perceive the fundamental vibrations of the cosmos itself. For decades it was a dream, a fantastical prediction on the chalkboards of theoretical physicists. We knew these waves must exist. Einstein's equations told us so. But they were predicted to be so impossibly faint, so infinitesimally small, that detecting them seemed a fool's errand. It would require an instrument of almost spiritual sensitivity, a machine capable of measuring a distortion in reality 1,000 times smaller than a proton. Building such a machine became a multi-generational quest, a testament to human persistence. It required lasers of impossible stability, mirrors polished to atomic perfection, and vacuum chambers emptied of all but the most stubborn atoms. Two immense L-shaped detectors were constructed thousands of miles apart, forming a single planet-sized antenna. They were called LIGO, the Laser Interferometer Gravitational Wave Observatory. And for years they listened. They listened to the silence, straining to hear that one final chirp from a cosmic car crash happening hundreds of millions of light years away. They were listening for the sound of spacetime itself. Then, on September 14th, 2015, the silence was broken. A signal arrived so clean, so perfect, so exactly what theory predicted, that the scientists who saw it first thought it must be a drill, a test injection. But it was real. A tremor that had been travelling for 1.3 billion years, launched into the cosmos when life on Earth was just single cells, had finally washed over our planet. It had passed through your body, through the core of the Earth, and in its final moments it had nudged LIGO's mirrors by a fraction of an atom's width, and we heard it. For the first time, humanity heard the music of gravity. It was a moment that redrew our map of the universe. We had been granted our new sense. The age of gravitational wave astronomy had begun. In the years that followed, we became cosmic listeners. Our detectors grew more sensitive, joined by others across the globe, creating a network of ears pressed against the firmament. We heard dozens of these cataclysms, the ghostly chirps of merging black holes and colliding neutron stars. Each detection was a discovery, a postcard from the extreme universe. We were cosmic archaeologists sifting through the gravitational rubble of events that had happened long ago and far away. We would hear a chirp and then the frantic work would begin. Where did it come from? How massive were the objects? What does this tell us about the universe's history? We were always reacting, always looking back, piecing together the story from an echo that had already faded. We were passively waiting for the universe to speak to us. But that is all about to change. Because we are on the verge of a revolution so profound it will make that first discovery in 2015 seem like a prelude. We're about to transition from listening to the past to witnessing the future. The year 2025 marks the dawn of a new audacious era. An era not of cosmic archaeology but of cosmic prophecy. The era of the gravitational wave alert. Imagine for a moment that instead of hearing a faint ghostly chirp from an event that happened a billion years ago, you receive a message. A cosmic telegram that says, get ready. In this specific patch of sky, two black holes are in their final spiral. In 3 days they will merge. Point your telescopes there. Point everything you have. This is not science fiction. This is the promise of 2025. Our gravitational wave detectors are reaching a level of sensitivity so exquisite that they will soon be able to hear the faint foundational hum of these binary systems, not just in their final screaming milliseconds, but for days, even weeks before they collide. We will hear the opening notes of the symphony, not just the crescendo. We will be able to track them as they spiral inwards, calculating their trajectory, their masses, their spin, and most importantly, predicting the precise moment and location of their inevitable catastrophic union. This is the Gravitational Wave Alert System, a planetary early warning network for the most violent events in the cosmos. It represents a complete paradigm shift in how we do astronomy. For the whole of our history, we have been accidental tourists in the universe. We would see a star explode as a supernova, a dazzling spectacle of light, but we were always late to the party. The light only reaches us after the cataclysm is already over. We were always studying the crime scene, never witnessing the crime. With these alerts, we will get a front row seat. For the first time, we can be proactive. We can receive the gravitational alert, the cosmic save the date, and mobilize every single astronomical asset we possess. The Hubble Space Telescope, the James Webb Space Telescope radio arrays spread across continents, X-ray and gamma-ray satellites in orbit. We can have them all pre-aimed, waiting, staring at an apparently empty patch of sky, holding their breath for a show they know is coming. We will be able to watch the entire event unfold in real time across the entire spectrum of existence. We will see the gravitational wave signal rise to its terrifying peak, and at the exact moment of collision we will search for the flash of light. Is there one? Theory says that the merger of two black holes should be perfectly dark. But the universe has a habit of surprising us. What if the collision is so violent it tears a temporary rift in the veil, unleashing some form of energy our theories have yet to dream of? We have never been able to look before. Now we can. And what of neutron stars? Those city-sized atomic nuclei left over from the death of smaller stars. When they collide, the gravitational wave alert will give us notice. We can watch as these ultra-dense objects tear each other apart, triggering a kilonover, a cosmic blast, where the universe forges the heaviest elements in its pantry. The gold in your ring, the platinum in a catalytic converter, the uranium that powers our cities, all of it was born in these fleeting, furious moments. We have seen the aftermath, but with the alert we can watch the forge itself in operation. We can test the limits of physics in a crucible we could never hope to replicate on Earth. The gravitational wave alert is more than just a new tool. It is an invitation to a cosmic appointment we have set for ourselves. It changes our relationship with the universe from one of passive observation to active participation. We are no longer just listening to the echoes of creation, we are anticipating its loudest roars, preparing to witness them live. This is a quest not just to see something new, but to understand something fundamental. Every one of these collisions is an experiment conducted on our behalf by nature itself. An experiment that probes the very essence of space-time, the nature of gravity in its most extreme form, and the origin of the matter that makes up our world. We are standing at a threshold. Behind us lies the quiet, dark era where the universe's most profound secrets were whispered in a language we could not hear. Ahead of us lies a new epoch, one filled with alarms and countdowns, where we can pinpoint the next great cosmic drama on a star map and settle in to watch the curtain rise. The year 2025 is not just another year on the calendar. It is the year we stop waiting for the universe to come to us. It is the year we learn to read its schedule and for the first time truly look it in the eye at its most violent, its most creative, and its most revealing moments. The questions we can finally begin to answer are the ones that haunt us the most. What truly happens at the edge of a black hole? Is Einstein's theory of gravity the final word, or will it crack under this strain? How did the supermassive black holes that anchor our galaxies come to be? The answers are out there, written in the language of gravitational waves. And we are at long last ready to receive the call. What if the universe is not what it seems? What if the vast silent emptiness between the stars is not empty at all, but a dynamic living entity? A substance that can be stretched, twisted and compressed by the cosmic dramas playing out within it. This was the sublime and terrifying proposition that a young Albert Einstein unleashed upon the world in 1915. He didn't just offer a new law of gravity, he fundamentally rewrote our definition of reality itself. Before him, we imagined space as a fixed, passive stage, an eternal backdrop upon which the planets and stars performed their predictable play. But Einstein's general relativity presented a cosmos of breathtaking intimacy, where matter and energy were not merely in space and time, but were actively shaping them. He showed us that a star doesn't just sit in the void, it tells the very fabric of space-time how to curve. A planet doesn't follow an orbit because of a mysterious invisible force pulling on it from afar. Instead, it travels along the straightest possible path through a universe that has been warped and contoured by the sun's immense mass, like a marble rolling around a deep well in a rubber sheet. This was a revolution in thought, a vision of a gravitational ballet where the dancers created the dance floor with every move they made. Yet buried deep within the elegant mathematics of this new cosmic architecture was a prediction, a consequence so strange, so ephemeral, that it bordered on the fantastical. If space-time could be bent and curved by mass, then what would happen if that mass were to be violently cataclysmically accelerated? Einstein's equations answered with a ghostly prophecy. They foretold of waves not of water or sound, but of the substance of reality itself. They predicted ripples in the geometry of the cosmos racing outwards from the most violent events imaginable at the speed of light. These were gravitational waves. Imagine two titans in a death spiral, two colossal black holes or neutron stars whirling around each other at nearly the speed of light. Their immense gravity wouldn't just be warping the space around them. It would be churning it, twisting it, flinging off waves of pure gravitational energy. These waves would be the universe's own shudders, the aftershocks of creation and destruction. They were not light nor any form of matter we could ever hope to touch. They were in essence travelling distortions of distance itself. As a wave passed through you, it would stretch and squeeze everything it touched first, elongating you in one direction while compressing you in another, then reversing the effect in an infinitesimally brief oscillation. You wouldn't feel it. You couldn't see it. It would be a phantom passage, a whisper from a cosmic calamity that had occurred millions or even billions of years ago. For decades, this profound idea remained just that, an idea, a ghost in the machine of relativity. It was a theoretical curiosity, a beautiful but untouchable artifact of the equations. Even Einstein himself, the prophet of this new reality, was deeply skeptical that we could ever build an instrument sensitive enough to detect such an impossibly faint signal. The universe, it seemed, was determined to keep its most profound secrets. The sheer, soul-crushing difficulty of the task cannot be overstated. We were trying to listen for a whisper in a hurricane to measure a tremor that was smaller than the smallest known components of matter. The effect of a passing gravitational wave, even one from a cataclysm of unimaginable power, would be to stretch and squeeze the very rulers we use to measure the world by a distance so minuscule it defies all human intuition. Imagine a ruler 4 kilometers long. A strong gravitational wave arriving from a nearby cosmic collision might change its length by just 1/10,000th the width of a single proton. This is not a challenge of engineering. It is a challenge that borders on the absurd a measurement that seems to violate the very limits of physical possibility. How do you measure a change in distance that is 1 billion times smaller than a bacterium and 1,000 times smaller than an atomic nucleus? The world around us is a constant storm of vibrations, the gentle hum of the Earth's own seismic activity, a truck rumbling down a highway miles away, the waves of the distant ocean crashing upon the shore, even the thermal jiggling of the atoms within the detector itself. All of these create a level of background noise that is trillions upon trillions of times louder than the signal we were hoping to find. It was a quest for a perfect, impossible stillness, a hunt for a signal buried so deep in the static of existence that finding it seemed a fool's errand. For much of the 20th century, the hunt was precisely that. Early pioneers like the brilliant and controversial physicist Joseph Weber constructed the first generation of detectors in the 1960s. These were not the sophisticated instruments we know today, but massive solid cylinders of aluminum weighing several tons. The idea was that a passing gravitational wave would cause the bar to resonate, to ring, like a bell struck by the hammer of spacetime itself. Weber claimed to have found signals sparking a brief and frantic period of excitement, but his results could never be replicated. The universe remained silent. His resonant bars, while ingenious for their time, were simply not sensitive enough. They were listening for an orchestra with an earplug. The decades that followed were a long, arduous journey through a scientific wilderness. Funding was scarce. The broader physics community was often deeply skeptical, viewing the quest for gravitational waves as a fringe high-risk endeavour, with little chance of success. It took a special kind of conviction, a stubborn, almost fanatical belief in both Einstein's theory and human ingenuity to persevere. It was a multi-generational quest passed down from one physicist to another, a quiet promise to one day build a machine capable of hearing the silent symphony of the cosmos. That machine, when its design finally began to crystallize in the minds of pioneers like Rainer Weiss, Kip Thorne, and Ronald Drever, was a concept of breathtaking audacity and elegance. It would not be a solid bar, but an instrument made of light itself. The new idea was called a laser interferometer, a name that belies the magnificent scale of its realization. The concept is simple in its genius, yet Herculean in its execution. You take a powerful laser beam and split it in two. You send each half of the beam down a very long, perfectly straight and completely empty pipe, arranged in a giant L shape. At the end of each pipe, kilometers away, is a mirror of almost supernatural perfection. The light bounces off these mirrors and travels back to the corner where it started, where the two beams are recombined. If the two arms of the L are exactly the same length, the light waves, when they meet again, will be perfectly out of sync and cancel each other out, resulting in darkness. This is the state of perfect silence, the instrument holding its breath, waiting. but if a gravitational wave passes through it, will stretch one arm of the detector while simultaneously squeezing the other. For a fleeting instant, one path for the light will be infinitesimally longer and the other infinitesimally shorter. The two returning laser beams will no longer perfectly cancel out. A tiny flicker of light will escape to a detector, a signal of a disturbance not in the machine, but in the very fabric of spacetime it occupies. This was the blueprint for the Laser Interferometer Gravitational Wave Observatory, or LIGO. But turning this elegant concept into a functioning machine required a war against the noise of our own world on a scale never before attempted. Two identical observatories were constructed 3,000 kilometers apart in the pine forests of Livingston, Louisiana, and the arid plains of Hanford, Washington. This was crucial. A true cosmic signal must arrive at both detectors, separated by the milliseconds it takes for the wave to travel between them, providing an unmistakable confirmation that the source was not a local tremor or a passing truck. Inside each 4-kilometer arm, a vacuum was created that is one of the most perfect on Earth, 1 billion times emptier than the air we breathe, ensuring that not a single stray molecule could jostle the laser beam. The mirrors, crafted from flawless fused silica and polished to an accuracy of less than a single nanometer, were the smoothest objects of their size ever created by human hands. They were hung from a complex multi-stage pendulum system, a gravitational gyroscope designed with layer upon layer of seismic isolation to insulate them from the constant shudder of the planet. Every component, from the laser's frequency stability to the electronic control systems, had to be pushed to the absolute extreme of technological possibility. LIGO was not merely a building with equipment inside it. The entire edifice, all 8 kilometers of its vacuum tubes, its lasers and its mirrors, functioned as a single unified scientific instrument of unprecedented sensitivity. It was a planetary-scale sensory organ, an ear forged from steel glass and light designed and built for a single purpose: to listen to the sound of spacetime itself. And it was not alone. Across the Atlantic, near Pisa, Italy, the Virgo detector, with its own 3-kilometer arms, was built in a similar spirit of audacious precision. Later, the Kagura Observatory would join the hunt from deep within a mountain in Japan. Humanity was building a global network, a celestial microphone array, to finally eavesdrop on the universe's most guarded conversations. After decades of design construction and painstaking calibration, the newly upgraded Advanced LIGO began its first official observing run in the autumn of 2015. The machines had been pushed to a sensitivity barely dreamed of by the project's founders. The teams were hopeful, but decades of silence had taught them a profound patience. They expected it might take months, perhaps even years, to capture the first definitive signal. The universe had other plans. On September 14, 2015, before the observing run had even officially begun, while the systems were still undergoing their final engineering checks, something extraordinary happened. A signal arrived. It appeared simultaneously in the data streams of both the Hanford and Livingston detectors, a clear, unambiguous tremor that stood out from the background noise like a shout in a library. It was not a glitch. It was not a random fluctuation. It was a perfect textbook waveform, a rising tone that swept upwards in frequency and amplitude over the course of just 0.2 of a second before abruptly cutting off. It was a sound translated from the vibrations of space-time into the language of our computers. It was a chirp. For the scientists who first saw it, it was a moment of heart-stopping disbelief. The signal was so strong, so clean, it was almost too good to be true. It looked exactly like the waveforms that theorists like Kip Thorne had been simulating on supercomputers for years, the precise signature predicted for the final violent moments of two black holes spiraling into one another. The chirp told a story of breathtaking violence, a saga that had unfolded over 1 billion years. Far away in a distant galaxy, two black holes, one about 29 times the mass of our Sun, the other about 36, had been locked in a gravitational dance for eons. They had been born from the collapse of colossal ancient stars and had spent their existence orbiting each other, their immense gravity churning the space-time around them, radiating away energy in the form of gravitational waves. As they lost energy, they drew closer, their orbit tightening, their speed increasing. In the final moments, they were circling each other hundreds of times per second and moving at more than half the speed of light, their event horizons whipping through a maelstrom of warped reality. The chirp was the sound of this final frantic spiral. The abrupt silence at its end was the sound of the climax the moment the two black holes touched their event horizons, merging to become one. In that last fraction of a second, the two objects with a combined mass of 65 suns coalesced into a single larger black hole of 62 solar masses. But where did the missing mass go? The numbers reveal a truth more staggering than any fiction. 3 entire solar masses, the equivalent of annihilating 3 stars identical to our own sun, in an instant had been converted directly into pure energy. Not light, not heat, but the raw, untamed energy of gravitational waves, a space-time shock wave that radiated out across the cosmos. For that brief moment, the power of this single merger outshone the combined light of every star and every galaxy in the entire observable universe. And for 1.3 billion years, that colossal burst of energy travelled unimpeded across the expanding void. It journeyed through intergalactic space past countless star systems and nebulae, its power dissipating with distance, its waveform stretching with the expansion of the universe itself. It finally washed over Earth on that September morning, a faint residual echo of a truly cosmic spectacle, and the 2 L-shaped machines built by a curious ape-descended species on a small rocky planet trembled by less than the width of a proton. The signal designated G215094 was real. The agonizing months that followed were a testament to the rigor of the scientific process. Every possibility of error was investigated. Every system was checked and rechecked. The team had to prove beyond any shadow of a doubt that this was not a terrestrial artifact, not a clever hack, not some bizarre, unforeseen source of noise. They had to convince themselves before they could dare to tell the world. When the announcement finally came on February 11th, 2016, it was a thunderclap that echoed through the halls of science and out into the public imagination. A century-old prediction, a ghost in an equation, had been made real. We had not only proven Einstein right in the most extreme environment imaginable, but we had achieved what he and generations of physicists after him had believed to be impossible. We had heard the universe. This was not simply the discovery of a new particle or a distant planet. It was the birth of an entirely new way of observing reality. For the entirety of human history, our knowledge of the cosmos had come to us through the medium of light. From the naked eye to the Hubble Space Telescope, from radio waves to gamma rays, every window we had opened to the universe was a window onto the electromagnetic spectrum. We were celestial photographers capturing the light from distant objects. But gravitational waves gave us a completely new sense. We were no longer merely watching the universe. We could now listen to it. We could hear its most fundamental processes, the collisions of objects that emit no light at all. We could finally access the dark side of the cosmos, the mergers of black holes, the collisions of invisible neutron stars, the secret violent lives of the universe's most enigmatic inhabitants. GW150 was the first note in a symphony that was just beginning. It was the moment astronomy evolved. The silence was broken, and with this newfound sense we turned our celestial ears back to the void, listening intently. The initial trickle of discoveries soon became a flood, each new chirp, telling us more about the life and death of stars, the nature of gravity, and the fundamental structure of the cosmos. But even as we grew accustomed to this new reality, our instruments were becoming ever more sensitive, pushing the boundaries of detection further still. And now, as we listen with a sensitivity far beyond what was possible in 2015, a new alert is sounding a new signal that promises to be unlike any we have ever heard before. The universe is about to tell us another one of its secrets. The thunderous applause for that first universe-shaking discovery had not yet faded when a collective unspoken anxiety began to permeate the labs and control rooms. Had we just witnessed a miracle, a singular, impossibly fortunate alignment of cosmic destiny and human ingenuity? Or was that first gravitational cry from 1 billion years past merely the opening note in a symphony we were only just beginning to hear? The universe, it seemed, was in no mood to keep us waiting. Just months later, another signal arrived, a fainter, more delicate tremor in the fabric of space-time. This was not a clash of titans like the first. This was different. It was the merger of two smaller black holes, one just 14 times the mass of our Sun, and the other only 8. They had danced their final doomed spiral. A little farther away, their parting shriek a testament to a different kind of cosmic violence. And with its arrival, a profound realization washed over the global scientific community. This was not a fluke, it was a population. The gates to the dark universe had not just been cracked open, they had been thrown wide. What followed was not a drip of new information, but a deluge. The era of gravitational wave astronomy had truly begun transforming from a quest for a single history-making event into a methodical, relentless survey of the universe's most extreme phenomena. The two LIGO detectors in America, our first ears to the cosmos, were soon joined by a crucial new partner. Across the Atlantic, nestled in the Tuscan countryside of Italy, the Virgo detector came online. Its addition was a monumental leap, a geometric necessity for turning this new sense of hearing into a true sense of sight. Imagine yourself in a dark room hearing a sudden sharp clap. With 2 ears you can get a rough idea of the direction, a general sense of left or right, front or back. But with a 3rd ear placed far away from the other 2 you can triangulate. You can pinpoint the source with astonishing accuracy. This is precisely what the LIGO-Virgo network allowed us to do. No longer were we simply detecting a wave washing over Earth, we were now tracing its path back to its cataclysmic origin, identifying a specific patch of the star-dusted sky from which it had travelled for eons. The hunt was on, and our map of the invisible cosmos was about to be drawn. As the observing runs progressed, each more sensitive than the last, the catalogue of cosmic cataclysms began to swell. What had once been purely theoretical, a fiction spun from the mathematics of Einstein's equations, was now becoming a veritable bestiary of cosmic monsters. We were conducting a census of the stellar graveyard, and its inhabitants were proving to be far more diverse and far more surprising than anyone had dared to predict. The black holes we were finding were on average perplexingly massive. Our theories of stellar evolution, the models that meticulously charted the lives and deaths of stars, had suggested that black holes born from collapsing stars should rarely exceed 20 or perhaps 25 times the mass of our Sun. A star massive enough to form a larger black hole would, according to the models, blow itself to pieces in a supernova so violent that it would leave nothing behind. Yet here they were in the data planer's day. Binary systems with black holes of 30, 35, even 40 solar masses locked in gravitational embraces that defied our neat and tidy explanations. Where were these behemoths coming from? How did they grow so large? Were our models of how stars die fundamentally incomplete, or were we witnessing the products of a different kind of cosmic life cycle altogether? Perhaps these weren't first-generation black holes. It's possible we were seeing the aftermath of previous mergers' 2nd or even 3rd generation cannibals that had grown by devouring their own kind within the crushingly dense hearts of ancient globular clusters. In these celestial cities with millions of stars packed into a space only a few light years across, black holes could sink to the core and engage in a chaotic demolition derby, merging and growing over billions of years. Suddenly, gravitational waves were not just confirming a theory, they were a powerful new archaeological tool allowing us to excavate the history of the universe's most crowded and violent neighbourhoods. The data forced a painful but exhilarating reckoning, compelling astrophysicists to return to their blackboards to question the very foundations of how the universe forges its darkest, most massive objects. The surprises, however, were not confined to the giants. An even deeper mystery began to emerge in the space between the known classes of cosmic corpses. For decades we had a clear demarcation. On one side you had neutron stars, the incredibly dense cinders left behind by smaller supernovae objects so compressed that a teaspoon of their substance would outweigh Mount Everest. But they had a limit. Physics dictated that a neutron star could not be more massive than about 2.2 times our Sun. Any heavier, and its own gravity would crush it into a black hole. On the other side were the black holes themselves, which we had assumed started at around 5 solar masses. In between these two realms lay a strange and forbidden desert, what astronomers called the lower mass gap. Nature, it seemed, did not build objects in this range, but nature, as we were rapidly learning, does not always obey our expectations. The gravitational wave detectors began to hear whispers from this very desert. Events were recorded that seemed to involve an object of roughly 2.6 solar masses, too heavy to be a neutron star, yet lighter than any black hole we had ever confidently identified. What was this thing? Was it the universe's lightest black hole or its heaviest neutron star, an object straining at the very limits of existence before its final collapse? The discovery was electrifying because it struck at the heart of our understanding of the supernova mechanism itself, the very engine of stellar death. The explosion that creates a neutron star is exquisitely different from the one that creates a black hole, and the boundary between them was thought to be a sharp, well-defined cliff. But these new discoveries suggested it might be a more gradual, messy, and far more interesting slope. We were finding the universe's exceptions the outliers that break the rules, and in science it is almost always the exceptions that lead to the most profound breakthroughs. Each new detection in this enigmatic mass range was another clue, in a cosmic whodunit, a puzzle that reshaped our view of the chaotic final moments of a star's life. The gravitational whispers from these strange in-between objects were challenging our neat categorization of the cosmos, forcing us to admit that the universe's imagination was far richer than our own. Then, on August 17th, 2017, everything changed. A signal arrived that was utterly unlike any we had heard before. It wasn't the brief violent whoop of two black holes merging. This was longer, more intricate. It was a chirp that lasted for over 100 seconds, climbing in frequency as two smaller objects spiraled relentlessly toward each other. The mathematics was unequivocal. This was not a black hole merger. This was a death spiral of two neutron stars. And this time, the universe didn't just send a wave, it sent a flare. Just one. 7 seconds after the gravitational wave peaked at the LIGO and Virgo detectors, a NASA satellite designed to spot gamma rays from deep space detected a short, brilliant flash from the same region of the sky. It was the smoking gun. For the first time in human history, we had both seen and heard the same cosmic event. This was the birth of a new era, the dawn of what we now call multi-messenger astronomy. The alert went out to a global network of astronomers. The LIGO-Virgo collaboration had done its job triangulating the source to a small patch of sky in the constellation Hydra. All across the planet, telescopes on mountains and in deserts in orbit, and on the ground slewed their gaze toward that one specific point. And what they saw was breathtaking. There in a galaxy 130 million light-years away, a new point of light was fading into view, an afterglow where none had existed before. We were witnessing in real time the birth of a kilonova. This was not just a collision, it was a spectacular act of cosmic alchemy. As the two neutron stars tore each other apart, they sprayed a vast cloud of raw, neutron-rich material into space. In this expanding fireball under conditions of unimaginable temperature and pressure, the universe's heaviest elements were being forged. It was a celestial furnace running a cosmic-scale nuclear reaction that created vast quantities of gold, platinum, uranium, and other elements heavier than iron. For you see, the great mystery of our cosmic origins had always been incomplete. We knew that stars like our Sun could fuse hydrogen into helium, and that larger stars could create elements up to iron. But beyond that, the origin of the universe's most precious materials was a subject of heated debate. The gold in your wedding ring, the platinum in a catalytic converter, the iodine essential for life, where did it all come from? That day we found the answer. We were watching the cosmic factory at work. The light from the kilonova told a remarkable story. Initially it glowed a brilliant blue, the signature of lighter, heavy elements being formed. Then, over days and weeks, it faded and reddened as the slower, more complex radioactive decay of the heaviest, most precious elements like gold began to dominate the light. We were watching alchemy on a scale that dwarfed the dreams of ancient kings. We had found the treasure chest of the cosmos, and it was forged in the wreckage of dead stars. This single event, GW1717, solved decades-old puzzles in one fell swoop. It confirmed the origin of short gamma-ray bursts it proved where most of the universe's heavy elements are made, and it even gave us an entirely new independent way to measure the expansion rate of the universe itself. It was perhaps the single most productive astronomical observation in history. The triumph of the neutron-star merger, however, cast a long shadow, one that highlighted our emerging limitations. As the detectors underwent upgrades and their sensitivity improved, the trickle of discoveries became a torrent, then a flood. During the third observing run, which began in 2019, the universe was no longer whispering, it was shouting. New mergers were being detected on average more than once a week. The sheer volume of data was staggering, a cacophony of cosmic collisions from every direction in the sky. Black holes merging with other black holes, neutron stars merging with neutron stars. And for the first time, we began to detect the ultimate mismatched pair, the collision of a black hole and a neutron star, an event where one object is simply erased from existence by its voracious partner. We were charting the full violent tapestry of compact object mergers. But with this incredible success came the sober realization that we were still only scratching the surface. Our ability to hear these events was beginning to outpace our ability to see them. For the more distant mergers, the gravitational wave signal was faint a whisper against the background noise of Earth itself. The triangulation from the three detector network, while revolutionary, still only narrowed the location down to a patch of sky that could be hundreds of times the size of the full moon. For astronomers trying to find a faint, fleeting afterglow with a powerful telescope that sees only a tiny sliver of the sky, at a time this was like searching for a single specific grain of sand on a vast beach. It was a frantic, often fruitless race against time. Too many events were happening too far away, their locations too uncertain to guarantee a successful follow-up with conventional telescopes. We could hear the thunder, but we couldn't see the lightning flash. We knew with chilling certainty that we were missing the kilonovas, the gamma-ray bursts, the explosive light shows that held the key to understanding the physics of these extreme environments. This growing frustration defined the new frontier. We had proven the principle, we had opened the window, but the view was still frustratingly blurry. The symphony of the cosmos was playing all around us, but we were listening with ears that were not yet sharp enough. To truly unlock the secrets revealed by events like the neutron star merger, to turn every gravitational wave alert into a rich, multi-messenger discovery, we needed more. We needed greater sensitivity to hear the faintest, most distant collisions from the dawn of the universe. We needed more detectors spread across the globe to shrink those search areas from the size of a celestial beach to a single grain of sand. We needed a data processing system so fast and so automated that it could alert telescopes not in minutes, but in seconds, before the precious afterglow of a kilonova had a chance to fade into the black. The incredible success of this golden age of discovery had paradoxically revealed our own inadequacies. It had laid bare the monumental challenge ahead. The crescendo of discoveries had set the stage, articulating a clear and urgent need for the next great leap forward, a generational upgrade in our ability to listen to the universe. A leap that engineers and scientists were already planning a more powerful global instrument, meticulously designed for the year 2025. To catch a ghost, you must first build a better trap. The early triumphs of gravitational wave astronomy had shown us the universe in a new light, a new sound. We had heard the final desperate chirp of colliding black holes, a whisper from the edge of creation itself. But these were echoes of events long past cosmic telegrams, delivered days, sometimes weeks too late. We were astronomers arriving at the scene of a cosmic cataclysm, only to find the embers cold, the evidence scattered. The greatest prize, the holy grail of this new science, remained tantalizingly out of reach to witness the collision itself, to see the explosion of light, the fireworks of matter that must accompany these gravitational death spirals. To do that, we needed more than just a listening post. We needed a global alarm, a celestial siren that could cry out the instant a wave was detected, mobilizing every telescope on and off Earth to turn its gaze towards the source before the afterglow faded into the black. This was the dream that fueled a revolution, a quiet, decade-long reimagining of what was possible. It was a challenge not just of bigger mirrors or more sensitive lasers, but of speed of intelligence, of a global symphony of engineering and software working in perfect, instantaneous harmony. The mission was clear: transform our detectors from passive cosmic ears into the nerve endings of a planetary-scale sensory organ, an interconnected system poised to give humanity its first real-time view of the universe's most violent acts. The journey began deep underground in the hushed, sterile vacuum tubes of LIGO Virgo, and their new partner Kaigro, nestled beneath a mountain in Japan. Here the very laws of physics set the ultimate limits on our perception. To hear fainter, more distant mergers, and to hear them sooner as they began their slow, inspiraling dance, we had to conquer a foe born from the heart of reality itself, quantum noise. Imagine trying to hear a pin drop in the middle of a hurricane. For our detectors, this hurricane is the constant restless jitter of subatomic particles, a quantum hiss that blurs the line between a real signal and phantom fluctuations of empty space. In previous observation runs, this noise was the fog of war, a shimmering veil that hid the faintest whispers. To pierce this veil, engineers and physicists embarked on one of the most delicate and ambitious upgrades in the history of science. They began injecting what is known as squeezed light into the detectors. This is a truly bizarre and wonderful feat of quantum engineering, a way of manipulating the very uncertainty of light itself. By squeezing the quantum uncertainty in one property of the laser light, say, its phase, they could reduce the noise in that channel, making the detectors profoundly more sensitive to the subtle stretching of spacetime. It was like giving a microphone a supernatural ability to filter out all background noise, leaving only the purity of the desired sound. You are in a very real sense cheating the quantum world at its own game, borrowing certainty from one place to create clarity in another. Simultaneously, the colossal mirrors, those 4.5-foot discs of flawless fused silica that act as the heart of the interferometers, received their own revolutionary makeover. Suspended by glass threads finer than a human hair, these mirrors must hang in almost perfect stillness, isolated from the ceaseless shudder of the planet. But even they are not immune to the quantum realm. The photons of the laser beam, billions upon billions of them, strike the mirror surfaces, and this barrage, this gentle rain of light, creates a subtle pressure that causes the mirrors to tremble. This is quantum radiation pressure noise, a faint, incessant drumming that can mimic the whisper of a distant black hole merger. To combat this, the mirrors were coated with new crystalline materials, dielectric layers engineered at the atomic level, to form a more perfect reflective surface, one that could quell these quantum tremors. The system for isolating the mirrors from the Earth's own seismic grumbling was also rebuilt from the ground up. A multi-stage pendulum system, a gravitational gyroscope of immense complexity, was installed, a cascade of steel and electronics designed to damp out every vibration from the crash of distant ocean waves to the rumble of a passing truck miles away. These detectors were being transformed into instruments of impossible sensitivity machines, so finely tuned they could feel a change in their 4-kilometer arms 1,000 times smaller than the nucleus of an atom. They were becoming quantum stethoscopes ready to listen to the faintest heartbeats of the cosmos. But this exquisite new sensitivity created a new monumental problem, a flood, a veritable tsunami of data. Every second, the upgraded detectors would pour out a torrent of information equivalent to thousands of high-definition movies. Buried within this avalanche of noise would be the prize, the faint rising chirp of a genuine cosmic event. Finding it in time was not a task for human eyes or ears. The challenge was no longer just about detection. It was about recognition, about teaching a machine to find a single specific needle in a perpetually growing haystack the size of a galaxy. And it had to do it in less than the blink of an eye. This is where the revolution moved from the physical to the digital, from the world of sublime engineering to the realm of pure, unadulterated computational power. At the heart of this new system lies a vast, ever-expanding library of ghosts. It's called a template bank, a catalogue of tens of millions of possible gravitational wave signals, each one painstakingly calculated by supercomputers, simulating every conceivable black hole and neutron star collision. There are templates for 2 small black holes in a gentle slow waltz, and for massive behemoths tearing each other apart in a violent final shriek. Each template is a perfect idealized waveform, a spectral ghost of a collision that might happen somewhere someday. The raw data from the detectors streams directly into a global network of high-performance computing clusters. Here, a new breed of artificial intelligence algorithm sharpened by machine learning acts as the first line of defense, the tireless digital sentinels. These AI are not just running simple comparisons. They have been trained on years of real and simulated data learning to distinguish the subtle signature of a true astrophysical event from the cacophony of terrestrial noise, the so-called glitches, that can plague the detectors. They are pattern recognition engines of extraordinary sophistication capable of identifying a potential signal as it rises ever so slightly above the quantum noise floor, long before it becomes an obvious chirp. As soon as these AI sentinels flag a candidate signal, the system kicks into high gear. The potential signal is instantly cross-referenced against the immense template bank. Specialized processors running in parallel across dozens of facilities race to find a match comparing the incoming data stream against millions of spectral ghosts simultaneously. Think of it as a cosmic game of Name That Tune, played in microseconds where the tune is the dying scream of a star and the prize is the fate of multi-messenger astronomy. When a match is found with a high degree of confidence, a moment of digital revelation, the true magic begins. The signal hasn't arrived at LIGO in Washington, LIGO in Louisiana, Virgo in Italy, and Kagra in Japan at the exact same instant. There are tiny, infinitesimal delays, mere milliseconds of difference caused by the time it takes the gravitational wave travelling at the speed of light to cross the Earth. These minuscule timestamps are the key. A purpose-built software colossus, a triangulation engine, ingests the data from all 4 detectors. By comparing the precise arrival times and the signal's characteristics as seen by each instrument, it can perform a near-instantaneous geometric calculation cross-referencing the points on the globe to triangulate the source's location on the sky. In the early days, this process took hours, sometimes days, of careful human analysis. The result was a vast uncertain patch of sky, hundreds of square degrees in area, a celestial haystack, within which astronomers had to search for the needle of an optical counterpart. But the new 2025 system is a different beast entirely. It is designed for speed and precision. The triangulation is automated, refined by algorithms that account for the Earth's rotation, the detector's varying sensitivity across the sky, and the specific signature of the matched template. Within seconds of the initial detection, it can shrink that search area dramatically, sometimes to just a few dozen square degrees. It generates a sky map, a celestial treasure map pointing the way to the cosmic crime scene. And this is the moment the entire system has been built for. The computational heart of the network doesn't just find the event, it tells the world. It automatically composes and sends an alert through the General Coordinates Network, or GCN, a global electronic telegraph system that has served astronomers for decades. But this is no ordinary message. It's an interstellar 911 call, a machine-to-machine shout across the planet. The alert contains everything: the precise time of the merger, the calculated distance, the likely masses of the objects involved, and most critically, that precious sky map. All over the world, in remote deserts, on frozen mountaintops, and orbiting high above the atmosphere, a silent robotic ballet commences. Dozens, soon to be hundreds of telescopes are subscribed to this GCN feed. Their own software instantly passes the incoming alert. Without any human intervention, observatory domes slide open. Massive robotic telescopes, from wide-field survey instruments to powerful deep space imagers, slew their mirrors towards the designated coordinates. They are programmed to begin taking images, immediately executing pre-planned observing strategies, searching for a new pinprick of light, the kilonova, the optical afterglow from a neutron star merger, or the flare from a black hole devouring its companion. The alerts also flash onto the screens of astronomers in control rooms from Chile to Hawaii, from Spain to South Africa. Teams on call who have been waiting for this moment scramble to verify the alert and command the world's largest observatories to join the hunt. Space telescopes like Hubble and the James Webb Space Telescope can be retasked. Their powerful eyes turn towards the new target. Radio arrays across continents can phase together to listen for the energetic jets that might be unleashed. High-energy satellites can search for the blast of gamma rays that signals the birth of a new black hole. This is the fulfillment of the multi-messenger promise. It is a global nervous system with the gravitational wave detectors as its sensory nerves, and the network of telescopes as its muscles, all coordinated by a brain of silicon and software. It is an organism of glass and steel and code spanning the planet, designed for the sole purpose of reacting to a tremor in space-time. The sheer scale of this coordinated effort is difficult to comprehend. It is the orchestration of countless independent systems, a testament to a scientific community willing to set aside individual goals for a collective purpose. Protocols were written, software interfaces standardized, and response times drilled to perfection. Teams ran endless simulations flooding the system with fake alerts to hunt for bugs and bottlenecks, ensuring that when a real wave arrived, the response would be flawless, instantaneous, and automatic. They had to be certain, because in this cosmic chase, every second counts. The light from these cataclysms can be breathtakingly bright, but also heartbreakingly brief. The initial flash might last only moments. The afterglow can fade below our detection limits within hours or days. The delay of even a few minutes could mean the difference between a Nobel Prize-winning discovery, a complete multi-wavelength portrait of a cosmic collision, and another cold trail, another missed opportunity. The engineering was sublime. The computation was revolutionary. The coordination was a masterpiece of human collaboration. Now all the pieces were in place. The upgraded detectors humming with squeezed light, their quantum hearts beating silently in the vacuum. The AI sentinels watching, listening, sifting through the endless river of noise for the one true signal. The global network of telescopes poised like sprinters in the starting blocks, waiting for the electronic starting gun. As the year 2025 dawned, a profound sense of anticipation settled over the global physics and astronomy community. The great machine was complete. The planetary sensory organ was online, its focus turned outward to the dark, silent expanse. They had built the trap and net woven from quantum mechanics, general relativity, and artificial intelligence. All that was left to do was wait for the ghost to appear, for the universe to scream, and for humanity, for the very first time, to be ready to see it happen. And so, with the dawn of this new era, the promise we spoke of transforms into a monumental challenge. The silent universe, which had only just begun to whisper its gravitational secrets to us, is about to begin shouting. The floodgates are opening. This is the reality of the 2025 Gravitational Wave Alert System, a global network poised to receive a deluge of cosmic revelations, a constant stream of news from the universe's most violent frontiers. What was once a once-in-a-generation discovery is on the verge of becoming a daily, perhaps even hourly occurrence. But this torrent of information, this gift from the cosmos, carries with it an immense and crushing weight. For every genuine whisper from a distant collision, there will be 1,000 false shouts, 1,000,000 distracting murmurs, a symphony of terrestrial and instrumental noise that threatens to drown out the truth. The pressure on the global scientific community is almost unimaginable. A palpable tension that now hums along with the detectors themselves. These men and women are no longer just astronomers or physicists. They have become cosmic detectives sifting through a relentless blizzard of data for the single perfect snowflake. Every 24 hours, the supercomputers linking LIGO, Virgo and Kagra must process a volume of information that would fill libraries hunting for that one specific vanishingly faint pattern. Characteristic chirp of two massive objects spiralling to their doom. But the universe is not a sterile laboratory, and our Earth is not a silent platform. The very ground beneath our feet conspires to deceive us. A passing freight train in Louisiana, its rumble vibrating through the soil, can subtly shake the mirrors of the detector. A distant earthquake on the other side of the planet sends seismic waves rippling through the crust, a planetary tremor that can masquerade as a cosmic one. Even the wind pressing against the long vacuum tubes can create a strain that mimics the stretching of space-time. These are the obvious imposters. The truly insidious ones are born within the machines themselves. They are known with a kind of weary familiarity as glitches. These are the instrumental spectres that haunt the data technological ghost that can perfectly replicate the signature of a real event. A sudden voltage fluctuation, a microscopic thermal variation in a piece of electronics, a rogue vibration in the complex seismic isolation system. Any of these can generate a phantom chirp, a false alarm that sends a jolt of adrenaline through the control rooms. Scientists have created entire catalogues of these glitches, giving them descriptive, almost whimsical names like blips, whistles, and taunts. They use sophisticated artificial intelligence machine learning algorithms trained on years of data to act as the first line of defense automated sentinels, tasked with separating the phantoms from the phenomena. Yet for every 1,000 glitches the AI correctly identifies and discards, there is always the fear of the one it will miss. The one real event, the whisper of a truly novel cosmic cataclysm that is mistakenly thrown away. Or worse, the one glitch so perfectly disguised, so cunningly similar to a theoretical signal that it fools both machine and human alike. Imagine the scene. A candidate signal emerges from the noise. It looks clean. It looks powerful. It has all the hallmarks of a binary neutron star merger, the very kind of event that could forge heavy elements and rewrite our understanding of nuclear physics. The automated systems flag it. A page goes out to on-call scientists around the world. In minutes, a frantic teleconference assembles experts from Germany, Italy, Japan, and the United States. They pore over the data, their screens filled with spectrographs and waveforms. For a few tense hours, they believe they have it. They're on the verge of triggering the global astronomical community, of initiating the greatest follow-up campaign in history. And then a junior researcher in Pisa, cross-referencing environmental monitors, finds it. A tiny anomalous magnetic fluctuation, recorded near one of the test masses 1/100th of a second before the signal. It was a glitch, a ghost. The colossal energy of a stellar collision, the creation of gold and platinum all reduced to a flicker in a circuit board. The collective hope evaporates, replaced by the grim necessity of logging the event, training the AI to recognise this new imposter and returning to the watch. This is the exhausting, nerve-shredding reality that precedes every genuine discovery. A battle of attrition fought against the noise of our own world. But when a signal survives this gauntlet, when it passes every check and is deemed a high-confidence event, the challenge only escalates. The real race begins. An alert stripped of all poetry is blasted out across the internet to thousands of astronomers. It's a string of code, a set of coordinates, a probability. It is the modern-day equivalent of a message in a bottle thrown from the wreckage of a cosmic cataclysm 1 billion years ago, finally washing ashore on Earth. And this message contains a treasure map. But it is a map drawn with a trembling hand on a canvas of unimaginable scale. Gravitational wave observatories, for all their sensitivity to the stretching of space-time, are profoundly poor at pinpointing where a signal came from. They are more like ears than eyes, hearing the thunder without seeing the lightning flash. The initial location of the event is not a precise point in the sky. It is a vast, sprawling smear of probability, a celestial search area that can be hundreds, sometimes thousands of times the size of the full moon. It is an impossibly large patch of cosmic real estate to search, and you must search it now, not tomorrow, not next week. The aftermath of these collisions, the brilliant fleeting flare of light known as a kilonova, is ephemeral. This blast of radioactive, newly forged matter shines brightly for only a few hours or days before fading forever into the background darkness of the cosmos. To miss this light is to miss everything. It's like hearing a colossal explosion in a distant city but arriving after the smoke has cleared left to wonder about the nature of the bomb. That light, that electromagnetic counterpart, holds the key to understanding the physics of the merger. It tells us what was made in the fire, where the heavy elements were forged. It confirms the models of nuclear astrophysics. It allows us to measure the expansion of the universe itself. Without it, the gravitational wave signal is just a sound in the dark, a beautiful but incomplete story. So the scramble begins. Across the globe, observatory directors and telescope operators are faced with a terrible decision. They must weigh the tantalizing possibility of capturing this fleeting cosmic ghost against the carefully planned observations they already have scheduled. Every minute on a major telescope is precious, booked months or years in advance by scientists with their own critical projects. To tear a telescope away from its planned target, from a decade-long survey of distant galaxies, or the patient observation of a planet-forming disk, is a monumental disruption. It is a gamble, a high-stakes bet, that this alert out of the dozens they might receive in a year is the one that will pay off. An astronomer in Chile halfway through a crucial exposure might see her night's work summarily cancelled by a target of opportunity override. An email arrives with the cold, authoritative coordinates of the search area. Her planned observation is halted. The great telescope, a marvel of engineering, slews across the sky, its giant eye now aimed at a patch of darkness, hundreds of square degrees in size, all on the hope of catching a flicker of light from a collision that happened when multicelled life was just beginning to emerge on Earth. This is a logistical nightmare of breathtaking complexity. The Earth itself becomes a barrier. The location of the merger might be setting in Chile, but it's rising over Australia. The coordination has to be seamless, a global ballet of machinery and human will. Radio telescopes in South Africa, vast arrays of dishes that can see the universe in wavelengths. Our eyes cannot must swing into action, searching for the afterglow of a relativistic jet punching its way out of the debris. Optical telescopes in Hawaii and the Canary Islands must begin a frantic brute force search, taking hundreds of wide-field images of the target area one after another. This is the cosmic equivalent of searching for a single, unique grain of sand on a vast beach in the middle of the night with the tide coming in. Their software will then compare these new images to older survey maps of the same region, looking for a new star, a transient point of light that wasn't there before. A single new dot among millions. Even our sentinels in orbit are called to action. An alert is uplinked to the Hubble Space Telescope, or the James Webb Space Telescope, or the Swift X-ray Observatory. Mission planners with only minutes to decide must calculate whether it is even possible to reorient the spacecraft, whether the target is in a safe viewing zone away from the blinding light of the Sun or Earth. Every second of fuel used to turn the telescope is a second taken from its operational lifespan. The stakes for these billion-dollar orbital assets are immense. A wrong move, a rushed commander could have catastrophic consequences. And all the while the clock is ticking. The kilonova is fading. With every passing hour its light dims and reddens, its precious spectral secrets smearing into ambiguity. If clouds roll in over the Andes, if a dust storm grounds operations in Australia, if a crucial satellite is on the wrong side of its orbit, the opportunity is lost. A window into the heart of a cosmic forge, a chance to witness the birth of the universe's heaviest element slams shut. Forever. We are asking our technology and our scientific collaborations to perform the ultimate cosmic heist. We must detect a ripple in spacetime from 1 billion years ago, triangulate its origin to a patch of sky containing millions of galaxies, coordinate dozens of independent observatories across 7 continents, and in space and point them all in the right direction within hours or even minutes, all to capture the faint fading glow from an explosion of unparalleled violence. The systems we have built to achieve this are a testament to human ingenuity and our insatiable desire to know. They represent a level of global cooperation unprecedented in the history of science. But they are fragile. They are subject to weather, to technology, to human error, and to the sheer crushing odds imposed by the scale of the cosmos. Every missed opportunity is a ghost that haunts the collaboration, a reminder of the secrets that remain just beyond our grasp. It represents a lost data point in our quest to understand where the gold in our jewellery or the uranium in our power plants truly came from. It is a failure to witness firsthand the behaviour of matter under pressures so extreme they can never be replicated on Earth. But every success, however rare, is a triumph for all humankind. It is the moment the thunder is finally paired with the lightning. It is the sound in the dark given a face, a location, a story. It is a single pixel of light in a new image that fundamentally realigns our place in the universe, a tiny beacon that illuminates the violent, beautiful and creative processes that ultimately gave rise to us. And as the 2025 alert system hums to life, sending out its steady stream of maybes and perhapses, the entire world of astronomy holds its breath waiting for the one that is real. But among the torrent of data, one alert is about to distinguish itself from the cacophony of glitches and standard issue mergers. It arrives not with the familiar, almost comforting signature of 2 black holes, nor the clean chirp of 2 neutron stars. It comes with something far more complex, something jagged and violent in its waveform. something that will test this global network and our understanding of the cosmos to its absolute limit. For a universe that contains such breathtaking violence, its most profound messages arrive in utter silence. They are not carried on light, nor are they shouted across the void. Instead, they are whispered into the very fabric of reality tremors, so faint, so impossibly delicate, that for all of human history they pass through our planet, through our bodies, completely unnoticed. Until now. And here in the hushed, sterile glow of the control room, amidst the quiet hum of machinery that listens to the cosmos, the silence is about to be broken forever. It begins with a string of text, a cascade of code scrolling across a monitor utterly devoid of fanfare, an automated alert triggered by an algorithm hunting for the ghost of a pattern within a torrent of noise. The designation is clinical, almost anonymous. Satu Thumfu a new event candidate. It's a message from half a universe away, a story that has been travelling for over 7 billion years, and it arrives on a Tuesday morning just before coffee break. At first, there is only professional calm. These alerts, after all, are the new normal. The upgraded network, our planet-sized ear, is now so sensitive that it registers a potential tremor every few hours. Most are phantoms, glitches born of earthly chaos. A distant rumble of thunder in the atmosphere, the subtle vibration of a freight train miles away, or even the quantum jitters of the laser mirrors themselves can conspire to create a forgery of a cosmic signal. The software pipeline flags them, assigns a probability and waits for a human mind to deliver the final verdict. Yet as the first diagnostic plots for Exum populate the screen, a different kind of quiet begins to descend upon the room. It's the tense electric silence of disbelief struggling against a rising tide of hope. On the screen, amidst the jagged random static of the background noise, is a shape so clean, so perfect, it almost looks simulated. It's the signature, the unmistakable sweeping upward curve of a gravitational wave chirp. You're seeing the sound of two massive objects locked in a final frantic dance, their orbital frequency accelerating with every pass. The curve on the screen is their song, a note rising in pitch and volume until it reaches a climactic universe-shaking crescendo, and then silence once more. The signal from the LIGO Livingston Observatory in Louisiana is there bold and clear. An ocean and a continent away, the Virgo detector in Italy shows the same beautiful, terrifying shape, arriving just milliseconds later, the slight delay, a crucial clue to its origin in the sky. Then, across the Pacific, the data streams in from the LIGO Hanford site in Washington state, confirming the event with its own identical signature. 3 detectors separated by thousands of miles have all just heard the exact same whisper from the cosmos at almost the exact same instant. The probability that this is a terrestrial glitch, a coincidence of local noise, plummets towards zero. This is real. This is from space, and it is loud. In the jargon of gravitational wave astronomy, its signal-to-noise ratio, the measure of its clarity against the background hiss, is colossal, far higher than anything seen before. Across the globe, phones begin to ring and encrypted messages flare to life. In a small apartment near Pisa, a physicist, just hours from ending her shift, abandons her dinner plans and races back to the control centre, her heart pounding with a mixture of adrenaline and scientific rigour. In a darkened home office in Washington, a data analyst is jolted awake by the piercing tone of a high-priority alert, his mind instantly racing to pass the preliminary data flashing on his tablet. This is the moment they have trained for the fire drill for a cosmic cataclysm. The first task is to rule out the impossible. Teams begin a frantic forensic investigation not of the signal, but of the Earth itself. They scrutinise every environmental sensor log from all 3 sites. Was there an earthquake anywhere on the planet, a lightning superbolt, a solar flare bathing the upper atmosphere in charged particles? Anything that could have minutely shaken the ground or disturbed the instruments in a correlated way across the entire globe? The answer coming back with painstaking certainty is no. The planet was quiet. The phantom was not of our world. With terrestrial causes ruled out the global collaboration, a symphony of hundreds of minds and machines pivots to the sky. The initial rough localization from the triangulation of the three detectors is crude, painting a broad patch of the southern sky, an area thousands of times larger than the full moon. Yet, it is enough. An electronic notice, a gamma-ray coordinates network or GCN circular, is automatically generated and blasted out to the astronomical community worldwide. On every continent, in mountaintop observatories and remote desert arrays, a new kind of frenzy begins. Robotic telescopes receiving the coordinates slew their massive mirrors toward that patch of sky, their digital eyes opening wide to hunt for a flash of light, an afterglow from the collision that might have generated these gravitational waves. Radio dishes swivel their sensitive receivers, straining to catch a burst of energy. Satellites in orbit reorient their sensors, searching for high-energy X-rays or gamma rays. It is a race against time, a global treasure hunt for a fleeting speck of light that could provide the missing piece of this extraordinary puzzle. The chances of finding such an electromagnetic counterpart from a pure black hole merger are slim, but for a signal this loud, this strange, no possibility can be ignored. While the world's telescopes stare intently at an empty patch of sky, the gravitational wave astronomers turn their full attention back to the signal itself. They have the sound, and now they must decipher the story it tells. The waveform is not just a simple curve, it is a rich tapestry of information, a message written in the language of spacetime. Its precise shape, the rate at which its frequency and amplitude increase, holds the secrets of the objects that created it. To decode it, they use one of the most powerful tools humanity has ever conceived, Albert Einstein's theory of general relativity. But the equations are far too complex to be solved by hand. Instead, they rely on vast libraries of pre-calculated templates, millions of possible gravitational waveforms, generated by supercomputers over years, each one corresponding to a different combination of black hole masses, spins, and orbits. The process is a form of cosmic fingerprinting. They must find the one template in this immense library that perfectly matches the signal S250714 that has just washed over the Earth. The initial automated analysis, the one that triggered the first alert, had already provided a rough estimate, and the numbers were jarring. They suggested the collision involved objects of enormous mass, far larger than the typical stellar mass black holes seen in previous detections. But those were just preliminary figures prone to error. Now the real work begins, a more meticulous and computationally intensive analysis, known as parameter estimation. Supercomputer clusters are tasked with the immense challenge running complex Bayesian algorithms that compare the observed data against the theoretical models over and over again billions of times, slowly and painstakingly narrowing down the possibilities. For the next few hours, the collaboration holds its collective breath. The data is beautiful, but the implications of those first rough numbers are so profound that they dare not yet be spoken aloud. It feels too much like a dream, the kind of perfect signal one might invent for a textbook, but never expects to see in the messy reality of nature. Then the results begin to solidify. As the computational models converge, a picture of the cataclysm begins to emerge from the digital fog, and it is more spectacular than anyone could have imagined. The event took place in a distant anonymous galaxy, nearly 7 billion light-years from Earth. This means the waves themselves began their journey long before our planet had even formed an echo, from a time when the universe was barely half its current age. They travelled across the expanding cosmos, their energy stretching and diluting over an unimaginable expanse, finally reaching our tiny world as a distortion in space-time 1,000 times smaller than the nucleus of a single atom. To have been detected so clearly from such an immense distance, the event itself must have been mind-bogglingly powerful. The models confirm it. In the final fraction of a second, as the two objects merged, they converted an amount of mass equivalent to more than 15 suns, directly into the pure raw energy of gravitational waves. For that fleeting instant, the merger shone brighter in gravitational waves than all the stars in the observable universe combined. It was a storm that literally shook the universe to its foundations. But it is the nature of the objects themselves that stops everyone cold. The numbers that come back from the analysis are not just big, they are revolutionary. The computer models, with increasing and terrifying confidence, report the masses of the two colliding objects. One of them clocked in at approximately 85 times the mass of our Sun. A true monster pushing the upper limits of what was thought possible for a black hole born from the collapse of a single star. Its partner, however, was something else entirely. The analysis places its mass at an astonishing 142 times that of the Sun. The number hangs in the air a challenge to decades of astrophysical theory. A black hole of 142 solar masses simply should not exist according to our leading models of stellar evolution. Stars in the necessary mass range are believed to tear themselves apart in a process called a pair instability supernova, leaving nothing behind, no black hole at all. They are predicted to inhabit a mass gap, a cosmic desert where black holes are not supposed to form. Yet here was the incontrovertible proof. S25071 Horn-Boret was not a collision between two stellar mass black holes. It was the merger of a very large stellar mass black hole with an object that sat squarely, undeniably, in the forbidden zone. It was the first direct detection of what was once a theoretical holy grail, an intermediate mass black hole. For decades, astronomers have spoken of them as the universe's great missing link. We saw the small ones, the stellar mass black holes left behind by dead stars weighing a few dozen suns. And we saw the supermassive ones, the gravitational anchors at the heart of every galaxy, weighing millions or even billions of suns. But we had never found the ones in between, the crucial stepping stones. How do you grow a billion solar mass monster? The leading theory was hierarchical, merging small black holes merged to form bigger ones, which merged to form bigger ones still in a cascade of collisions over cosmic time. Finding an intermediate mass black hole would be the first concrete evidence for this process, like finding a fossil of a teenager, to connect the baby to the adult. An S25071 Monterey was not just the fossil, it was a snapshot of the process in action. The two objects spiral together to form a final single black hole of roughly 220 solar masses, a newly minted member of this elusive class of cosmic objects. Suddenly, the silence from the sky made perfect, horrifying sense. We weren't just listening to the death of stars, we were listening to the birth of a monster. We were eavesdropping on the very process that builds the galaxies. This single event provides a mechanism, a pathway for creating the seeds of supermassive black holes in the early universe. Perhaps in the dense, chaotic environment of ancient globular clusters, stars and stellar black holes collided and merged repeatedly, building up their mass generation by generation, climbing the ladder until they reached this intermediate stage. From there, they could sink to the center of their host galaxy, continuing to feed and grow, eventually becoming the titans we see today. This wasn't just another detection, it was a Rosetta Stone for galactic evolution. In control rooms around the world, the quiet hum of the machines is now punctuated by hushed, awe-filled conversations. The verification process is long and arduous, with independent teams reanalyzing the data from scratch to check and recheck every last detail. But the signal is too strong, the data too clear. There is no other explanation. The truth of it begins to settle in a weight of discovery so immense it feels physical. For 7 billion years, the story of this impossible collision has been rippling across the cosmos, a silent testament to the laws of gravity. And for a few frantic, brilliant hours, a species on a small blue planet, armed with curiosity and instruments of unimaginable precision, finally learned how to listen. You're there in that moment of revelation. You are witnessing the map of the universe being redrawn not in the gentle strokes of theory, but in the indelible ink of observation. The ghost in the machine has just revealed a fundamental secret of our cosmic origins, a secret that now poses 1,000 new questions for everyone it has answered. The silence has been broken, and the universe will never sound the same again. And so, the storm has passed. The twin titans of space-time, after a billion-year spiral of death, have finally merged into one, their final violent scream now echoing away into the eternal silence of the void. But here on Earth, the silence is filled with a different sound. It is the sound of frantic activity of data streaming from telescopes on every continent and in orbit above. It is the sound of discovery, the hum of 1,000 minds working in concert, piecing together the ghost of a collision that occurred when the most complex life on our world was still algae. The 2025 Gravitational Wave Alert was not just another signal, it was a detonation, a moment that cleaved our understanding of the cosmos into two distinct epochs, before and after. Before we were passive onlookers, cosmic archaeologists sifting through the cold, ancient light of long-dead events, forever arriving late to the scene of the crime. We would find the wreckage a supernova, remnant a gamma-ray burst's afterglow, and from that fossil evidence we would try to reconstruct the cataclysm. We were astronomers of the past tense, but now everything has changed. The alert system, that global network of sentinels listening to the heartbeat of spacetime, has given us a profound new gift, the power of anticipation. We are no longer just looking at the universe. For the first time, we are listening to it in real time. The ripples in gravity travelling unimpeded at the speed of light became our celestial air raid siren, a cosmic tripwire, warning us that something unimaginable was about to happen. And because of that warning, when the final ferocious merger unleashed its torrent of light, its gamma rays, its X-rays, its every flavour of electromagnetic fury, we were ready. We were watching. Every major observatory on and off this planet turned its gaze towards that single insignificant patch of sky, waiting for the ghost to appear. This is a transformation more fundamental than the invention of the telescope. It is a shift from being cosmic photographers capturing static images of the past, to becoming cosmic seismologists feeling the tremors of the present as they unfold across the galactic stage. We have in essence grown a new sense, a sense that does not rely on light, which can be blocked by dust and gas, but on the very geometry of existence itself. It is a sense that allows us to perceive the universe's most secret, most violent and most fundamental dramas, the ones played out in absolute darkness. This new power was not born overnight. It is the culmination of a journey that began over a century ago, in the mind of a single man armed only with paper, a pen, and a thought experiment. When Albert Einstein first predicted these gravitational waves, they were little more than a mathematical ghost, a subtle tremor in his beautiful, elegant equations of general relativity. He himself doubted they would ever be detected. So faint was their predicted signature, a distortion of space smaller than the width of an atomic nucleus stretched over a detector several kilometers long. For decades, his theory remained an abstract masterpiece, a description of gravity so perfect yet so difficult to prove in its extremes. It was a whisper in a hurricane, a ripple from a pebble dropped in a cosmic ocean, seemingly destined to be lost forever in the background noise of the universe and our own world. But humanity is a stubborn species. The dream of hearing the whisper persisted, passed down through generations of physicists and engineers. It drove them to pursue an engineering challenge of almost absurd difficulty. They had to build the most sensitive measuring devices in human history. They had to silence the roar of the Earth itself, the crashing of distant ocean waves, the rumbling of trucks on a highway, the seismic jitters of our own planet, all to hear that one impossibly faint celestial note. For 50 years the search yielded nothing but silence. Skepticism grew. Many wondered if the quest was a fool's errand, a multi-billion-dollar effort to find something that wasn't there, or was simply too weak to ever be found. Then in 2015 the silence was broken. A faint rising chirp lasting less than a second swept through the LIGO detectors. It was the sound of two black holes 30 times the mass of our Sun colliding a billion light-years away. Einstein's ghost was real. The whisper had finally been heard. That first detection was our awakening. It proved the technology worked, it proved black holes existed in pairs, and it confirmed one of the most profound predictions of modern science. But it was just a prelude, a proof of concept. The 2025 alert was the symphony. It was the moment our new sense came of age, graduating from a single stunning discovery to a tool of routine, predictive, multi-messenger astronomy. It was the fulfillment of the century-long promise, transforming an abstract mathematical curiosity into a revolutionary new window through which we can now witness the universe in its rawest, most elemental form. And through that window, our conception of reality is being rewritten. Consider the black hole itself. For so long it was an object of pure theory, a mathematical monster hiding behind an event horizon from which nothing, not even light, could escape. We could infer their presence by the waltz of stars orbiting an unseen partner, or the superheated glare of matter spiraling to its doom in an accretion disk. But we had never witnessed their true nature, their lives, their dynamics, their deaths. The gravitational waves from the 2025 collision have changed all of that. These waves are not light from the black holes. They are the black holes. They are a direct manifestation of the object's mass, their spin, their violent motion encoded into the very fabric of space-time. Listening to the shape of that wave, its frequency and amplitude, we can measure these celestial predators with astonishing precision. We can test the bedrock principles of their existence, like the no-hair theorem, which predicts that a black hole is defined only by its mass, its spin and its charge. Any other hair, any other complexities should be radiated away. With each merger we are stress testing Einstein's theories in the most extreme environments imaginable, searching for the slightest deviation, the faintest unexpected tremor that could signal the presence of new physics, a crack in the foundations of our understanding. These are no longer static solitary beasts. We now see them for what they are: dynamic evolving engines of creation and destruction, gravitational gyroscopes that warp the universe around them, whose collisions are the most energetic events since the Big Bang itself. And in doing so, we are probing the nature of gravity itself. We have been bound by gravity our entire lives, stuck to this planet, orbiting this star, trapped in this galaxy. Yet we have only ever experienced its gentle, civilized side. The 2025 merger showed us gravity in the raw, in its untamed, relativistic state. It is not just a force, it is a medium. It is a fabric that can be twisted, stretched, and compressed. It is a tempest on the cosmic ocean, and for the first time we have built a ship that can sail those waters and a barometer to measure its fury. These waves are a pure manifestation of gravity, carrying an unfiltered message directly from the heart of the cataclysm, a message that tells us not just about the objects that created it, but about the fundamental nature of the space and time that carried it to us across 1 billion years. The event was also a cosmic crucible, an alchemical forge hotter and denser than anything we could ever hope to create on Earth. When the two objects finally touched, they didn't just merge, they rang space-time like a bell, and in that fleeting violent moment the laws of physics were pushed to their absolute breaking point. The shower of light and matter that erupted from that collision, the colour nova we so desperately trained our telescopes on, was a Rosetta Stone for extreme nuclear physics. Within that fireball, we witnessed the rapid neutron capture process, the very mechanism responsible for forging the heaviest elements in the universe. The gold in your jewellery, the platinum in industrial catalysts, the uranium that powers our reactors. We now know with certainty that these precious heavy atoms are born in the death throes of colliding compact objects. You're in a very real sense wearing the ghost of a cosmic collision. The 2025 alert transformed this theory into an observable fact, allowing us to match the gravitational signature of the merger with the specific electromagnetic signature of heavy element creation. We're no longer just theorizing about the universe's factories, we're watching their production lines in action, and yet this is only the beginning. The era of anticipatory multi-messenger astronomy has just dawned. Our current generation of ground-based observatories, LIGO, Virgo, Kagura, are magnificent, but they are tuned to hear only the high-frequency screams of stellar mass black holes and neutron stars in the final frantic seconds of their lives. There is a whole other universe of gravitational sounds to which we are still deaf. It is a low-frequency universe, a place of slow, ponderous cosmic bass notes. This is the realm of the supermassive black holes, the galactic titans millions or even billions of times the mass of our Sun, which lurk at the heart of nearly every major galaxy, including our own. When these behemoths collide, their death spiral takes not seconds but millions of years. The waves they produce have wavelengths so vast they would wash over our planet without the ground-based detectors even noticing. To hear this slow cosmic symphony, we must go to space. This is the vision behind LISA, the Laser Interferometer Space Antenna. It will be an observatory unlike any other ever built. 3 spacecraft flying in a perfect triangular formation, separated by 2.5 million kilometers of empty space. They will trail the Earth in its orbit around the Sun, linked by laser beams of unimaginable stability. This colossal triangle will be our net designed to catch the gentle, long wavelength swells of colliding supermassive black holes from across the universe. LISA will not just hear an event, it will hear the entire cosmic history of galactic formation. It will allow us to watch as galaxies merge and their central black holes begin their long gravitational dance, a performance that shapes the evolution of every star and planet within them. It will detect the ripples from countless smaller objects, white dwarfs and neutron stars spiraling into these giants, mapping the warped space-time around them with exquisite detail. LISA will open a window onto the dark side of the universe, revealing the gravitational skeleton upon which the cosmos of light is built. And back on Earth, the ambition is just as grand. The next generation of ground-based observatories is already being designed. The Einstein telescope in Europe, a vast underground triangle of detectors with arms 10 kilometers long, and Cosmic Explorer in the United States, a gargantuan 40-kilometer facility. These instruments will be so sensitive they will transcend discovery. They will not just detect the loudest, closest events, they will detect everything. They will hear every binary black hole and neutron star merger out to the edge of the observable universe. The cosmos for them will not be silent with occasional chirps. It will be a constant roar, a background hum of gravitational noise from a million simultaneous collisions. The challenge will no longer be about making a discovery. It will be about cataloguing an entire population, about teasing out the individual stories from the roar of the cosmic crowd. It will be the moment gravitational wave astronomy becomes gravitational wave sociology, allowing us to take a census of the most extreme objects in existence, charting their births, their lives, and their violent deaths from the dawn of time to the present day. We stand at a precipice of understanding. Behind us lies a century of brilliant theory and heroic engineering, ahead a future where we can see the unseen and hear the silent. The 2025 alert was the first breathtaking glimpse into that future. It armed us with a new sense, a new capability, a new way to question the cosmos. And the questions we can now ask are the most profound of all. Will these future observatories finally reveal the nature of dark matter and dark energy? Will they detect the faint primordial gravitational waves from the Big Bang itself, the echo of creation, a baby picture of the universe in its first moments? Could we find evidence of exotic objects like cosmic strings or wormholes whose gravitational signatures would be unmistakable? Or will we perhaps find the one thing we're always searching for in the deepest parts of the night sky, a crack in Einstein's armour? A subtle anomaly in a waveform, a slight deviation from prediction that hints at a new, deeper, and more complete theory of gravity. One that finally unifies the world of the very large with the bizarre rules of the quantum realm. That is the ultimate prize. The quest that began with a thought experiment has led us here to the edge of a new cosmic ocean. We have tasted the salt of its waters, we have felt the power of its tides, and we have built the first ships capable of leaving the shore. The journey ahead is long and the waters are deep. But for the first time in human history, we're no longer looking at the stars and wondering. We're listening to their stories, feeling their vibrations, and participating in the grand unfolding narrative of the universe, ready for the next alert, the next tremor in space-time, the next whisper from the dark.